Hello. Okay. Yeah, I will be super heuristic for this talk, and I hope people across the field can understand. And yeah, feel free to interrupt. Let me start with the explanation of the title. So, what is quantum anomaly? Well, if you ask your favorite chatbot or just open a textbook, quantum anomaly refers to the breakdown of classical symmetry upon quantization. Well, it's a bit abstract. Let me make it slightly more concrete. So, for instance, in the path integral, you have a symmetry for the action, for the classical action. It might break under the path integral after you do the horrible integration. Well, it's still super abstract, at least to me. So I would like to explain what it really means in a concrete example. Well, that's the example Zijian has mentioned. That's a quantum Hall effect. But I'm going to use the integer quantum Hall, which don't have any anion. So it's all electrons moving around in the magnetic field. Okay, so the final point is the edge of the quantum Hall effect has a chiral anomaly. Let's see how it show up. So we have some magnetic field coming out like perpendicularly penetrating the material. So it's a 2D material, and there's a magnetic field coming out. The electrons will just wind around the fluxes. But when they encounter the edge, they will bounce back. So effectively, you will encounter a scenario that on the upper edge, you have right-moving electrons, and then on the lower edge, you have left-moving electrons. So that's the classical picture. So what happens if you quantize it? Well, that's also simple. You have electrons, you have Schrodinger equation writing on the top line. So for instance, you have some boundary condition eigenvalues are discrete. So you have some picture like this. Okay, then you need to decide how to field electrons, how to field single particle energy levels. Okay, let's set some chemical potential. The chemical potential, some kind of property of the bulk material. Okay, then I decided to fill the energy level to a certain level. Let's say it's 0. Okay. So that's the quantum mechanical picture. So the vacuum will be just a Fock space occupied by all the electrons with, say, negative energies. That's a textbook picture for the Fermi sea. What's wrong with it? Well, if you really look at the edge, look at the chiral edge, you encounter some problem when you try to apply some background magnetic field. Background electromagnetic field. So if you apply an electric field along this direction, let's see the electric field coupled to the Schrodinger equation for the electron through the vector potential. So vector potential will be, so E will be minus dA dt. So there will be a increasing of the vector potential along this direction. And you can view this vector potential as a boundary condition for the electrons in this one-dimensional system. So when you changed vector potential, is like continuously changing the boundary condition. And when you change the boundary condition, you change your quantization condition. So your electrons in this picture can move around. And when you continuously change, it will just move up, up, up. And in the end, when the amount of time you apply the electric field happens to make the total change of boundary condition to be 2 pi, you will end up with the same Schrodinger equation, but the ground state will be there will be an electron moving up, so we'll have an extra electron. So that's the anomalous phenomenon. So you start with something. You start with a classical equation motion that preserves the charge, but when you try to apply electric field on it, and when the amount is 2 pi, you get an extra charge. So for the 1D animal living on the edge, it got confused. So where's the edge come from? well, we at least can see the 2D picture. For 2D animal, we will see it's actually coming from a bulk. So there's no real contradiction from the 2D perspective. How to see that? One simple way is just remember we are dealing with a whole system, like whole effect system. The phenomenological description of the whole effect is when you apply electric field in one direction, you should gain some current in the other direction. So in the direction perpendicular to it. So when you apply electric field for the whole system, and you should expect some electron go into the edge. So that will be the 2D explanation of the edge anomaly. So from 2D perspective, everything looks fine. Okay, so that's the type of anomaly I'm going to talk about today. So, not exactly the final like a new result is about, but that's the flavor of the anomaly. That's what I mean by quantum anomaly. You can also phrase it into modern language. So in the modern language, chiral anomaly can be phrased as a mixed 't Hooft anomaly between the vector potential and the vector potential and the axial potential. So vector field and the axial field. So if you are familiar with the QED calculation in the 3+1D, the standard textbook calculation for the axial anomaly or chiral anomaly is when you assume the vector gauge is never broken. That is basically assuming the Fermi sea is always filled, so you won't have an empty hole. Then the axial gauge has to be break. So in this context, the mixed anomaly means the symmetry flux will carry the charge. Well, in this context, it's easier to see. It's just rephrasing the source of the electric field. So we can apply electric field like dA dt, or we can just imagine we insert a magnetic flux in the bulk and increase the strength of the flux. So that will induce the electric field according to the Maxwell equation. But for the whole system, when you insert an extra magnetic flux, you will bond the extra charge here. So that's what brings you an extra charge to the whole system. So the slogan here is the symmetry flux actually will carry a charge for the anomalous system. Okay, great. Let's put some remarks here. So we come back to, so from the edge perspective, we found that the charge is not conserved. Let's go back to the textbook. So that's consistent with the textbook definition. A classical symmetry got broken upon quantization. Well, in some sense, it's kind of not satisfying because we are just hiding the charge in the abstraction of infinite dimensional hyperspace. I'm not a big fan of the infinite dimensional hyperspace. I want something more concrete. Let's think about some one-dimensional lattice system. Can we say something about it? Actually, if you try to formalize this chiral anomaly on the lattice system, where you cannot hide your charge into the infinite dimensional hyperspace, like the infinitely deep Fermi sea, you encounter a problem, which is actually nice. You have some topological constraint on the lattice Hamiltonian. The problem is when you try to regularize the theory on the lattice, well, it's a simple exercise for any condensed matter student. You just write down the Hamiltonian and diagonalize it and see the band structure. You will see that you have to go back. So it's like you cannot go infinitely deep in the Fermi sea, you have to come back. So that also means you have nowhere to hide the extra charge. So when you apply the same argument, you have a charge coming out, you have to have another charge coming down. So the charge is always conserved for the one-dimensional lattice model. It's basically the instance of the famous fermion doubling theorem. In the 1D, you have to have at least two chiral mode. You can never have one. So it puts a interesting topological constraint on the lattice Hamiltonian. Is it the end of the story that we will never encounter any interesting anomalies in the 1D lattice system with finite dimensional hyperspace? No, that's not all the anomalies has to be Bloch boundary. So you don't have to have some kind of Bloch system to hide the charge. You can actually talk about anomaly in the one-dimensional, like full-fledged one-dimensional theory. So that will be the type of anomaly I'm going to talk about today. Any question about this elementary?
The distinction like which anomalies can you realize in the same dimension?
Yeah, there's somehow the anomaly I'm talking about involve translation. So when you have that kind of translation symmetry involved, you can get rid of the higher dimensional interpretation. Otherwise, you end up with some kind of bulk inflow. Like there's a slogan in the high energy to half the anomaly is coming from bulk inflow. Yeah. But it's not true for our example, which involve translation symmetry. Okay, great. The type of anomaly I'm going to talk about is related to the Lieb-Schwarz-Matisse theorem. So let's just call it LSM anomaly. So the theory is very simple, has a very simple setting, and it's kind of very physically motivated setting. Just consider a one-dimensional spin chain with half integer spin. Let's say 1/2. So let's spin 1/2 for each site, and let's say periodic boundary condition for simplicity. So we have a translation symmetry, and we impose SO3 rotation symmetry for the possible Hamiltonians. The claim is quite strong. It's an older theorem, like more than 16 years ago. It says such a system cannot have a unique gap symmetrical ground state. Okay, let's make our logic simpler. Let's always assume we don't have symmetry breaking. Okay, then the claim is if this is your ground state, there must be a nearby excited states. The gap between them, the accurate statement is it has to be bounded by 1/L, but you can just say it's small. I mean, when it's going to 0 when the system size goes to infinity. So it's kind of gapless in the heuristic sense. It's a quite a strong theorem because we don't assume much, right? We just assume it preserves symmetry, and the representation is spin 1/2. Go ahead. That's when system size goes to infinity. For the final system size, what they showed is the gap is a scale, so at least at most 1/L. So, okay, how it works? Well, you probably want to, since I already mentioned the slogan, the symmetry flux carries charge. Let's try to devise a symmetry flux. Actually, that's what they originally do in the 16th paper. I mean the paper back in 16th. So they define something called a twist operator. The twist operator is doing a very simple thing. So you choose a preferred direction. You just choose whatever direction. Let's say Z direction. Since it's SO3 symmetric, it doesn't matter which direction you choose. And then apply this operator to your system. So what it does, so you rotate around the Z-axis with gradually increasing angle. So the first one will be rotated by 1/2 pi, and then the last one will be a full rotation, 2 pi rotation. Okay. Now we need to show that this symmetry flux is actually the symmetry flux of the U1 subgroup of SO3, but that's just the flux of the symmetry. Let's show it carries some momentum. Sorry, it carries some charge over another symmetry, which will be the translation symmetry. So what we really want to say is this 2 pi flux carries momentum. how to see that? I mean, if you, for those people who are not condensed matter background, at least for me in the beginning, before I see the proof, actually it's quite surprising to me that how such a simple operator can be argued to carry some definite charge of something else. But it works. Let's see how it works. So here is the twist operator, which you pictured as a 2-pi flux of the symmetry. And let's try to see its algebraic relation with the translation operator. So let's try to conjugate it by the translation. So what you do, literally, you just move everything by one lattice constant. Okay, then you get some operator look like this. This operator can be connected back to the original one by a global SO3 rotation, the Z rotation by 1 over 2 pi. So we rotate it back. Everything go back except the last one. The last one differs by what you have in the beginning with a 2 pi rotation. So now, just like many other non-trivial interesting phenomena in quantum mechanics, here the punchline is 2 pi rotation for spin 1/2 is -1. From the wave function or from the representation of the group, 2 pi rotation doesn't send you back. It sends you to -1. So which means these two operators anti-commutes on any SO3 symmetric states. In other words, you realize that if you start from a SO3 symmetric state, you apply this operator, the translation eigenvalue get a minus sign. So these two states have opposite, so have different momentum. Maybe you can say it like a momentum shifted by pi. In other words, you just pick any states that respect the symmetry, then you always find another state orthogonal to that that's created by this twist operator. But on the other, doesn't change much energy. So for any local Hamiltonian, what this twist operator do is slightly change the angle for the nearest neighbor. For instance, you have some kind of 1 over 2 pi, so 2 pi over L angle shift. So let's say you calculated energy change, so that will be 1 minus cosine 2 pi over L, which scales like 1 over L. And you have L turn over them, so you have 1 over energy gap between these two states. Well, it works for any states, but it's most interesting for the ground state. For the middle of the spectrum, you would expect the energy gap is not large anyway. So the interesting statement is about the ground state. So that's the LSM theorem. Okay, so that's the type of anomaly I'm going to talk about, the LSM anomaly, and how it works how it generalizes to the mixed states. That will be my research topic. Any question about the heuristic background part? Good. Now, at this moment, I hope we all have a sense that anomalous symmetry puts non-trivial constraints on the ground states. That's the lesson we learned over the past many decades. That say chiral anomaly puts non-trivial constraint on the lattice Hamiltonian, and this LSM anomaly put non-trivial constraint on the lattice. And they're actually quite useful. For instance, the LSM, when you generalize to 2D, there's one more possibility to have topological order. And this 2D version of LSM actually guides us to find the quantum spin liquid material. So it has real practical applications. Today, I'm going to extend this kind of thinking to the open systems, to the mixed states. The underlying logic is all these anomalies is about the symmetry and the representation, which the structure of a hyperspace doesn't really care which kind of states you talk about in such hyperspace. So the intrinsic structure in the hyperspace and the symmetry. So it's more like a mathematical fact. The talk today will be based on 3 papers, but mainly first two. First one is a work with my colleagues at Tsinghua and students there. Second one is a collaboration with Shen Hanjiang's group at Kafli Institute for Theoretical Science, also in Beijing. The third one is again a continuation of the collaboration, which talk about a slightly different aspect of the anomaly related to Tiber's question. So it's more like bulk boundary type of anomaly. It's related to the Z2SPT, like two-dimensional Z2SPT. Okay, from pure to mixed, so we have new problems. But why should we care about mixed states in the first place? So for conventional condensed matter setting, we are all working with the like material science experiments. So in material science experiments, most of the material in nature are actually in a good equilibrium. So we really care about the Hamiltonian. Hamiltonian determines the state in most cases. Say we encounter some ground state of a quantum Hall Hamiltonian, fractional quantum Hall Hamiltonian, there's a huge gap. So you don't really need to worry about any excited state and mixed states. And in some other experiment, we expect a good thermal equilibrium of the material. So you again, the state you talk about, if it's a mixed state, is kind of a thermal state, which is not independent data. It's kind of derived from the Hamiltonian, so e to the minus beta h. So you can just focus your research on the Hamiltonian, not worry much about the states. But for the audience here, we are very well aware that we are in the kind of a new era with quantum simulators and quantum computers. So in quantum simulators, the situation is quite different. You can devise some kind of Hamiltonian, but unfortunately, the initial state we start with, or the initial states in a quantum simulator are quite limited. And they're often low entangled states, like product states. For instance, the big point in the quantum scar I appreciate is that even from such kind of low entangled states or product states, there are interesting dynamics associated with that. So we don't have a good equilibrium state to start with. So often we need to deal with some complicated quantum dynamics. And another situation is you don't even have the Hamiltonian to talk about in the first place. So for instance, you create some quantum states from a quantum computer. So it's coming from a quantum circuit, which may also have noise in measurement or things like that, cannot be described by a simple Hamiltonian. So when we try to discuss physics for this kind of setting, we need to switch gear from Hamiltonian-centered research to kind of state-centered research. That's the goal today is to describe a characterization of the density matrix independent of modeling the environment. Just talk about the density matrix when it have the symmetries. So what can we say about the states? Okay, so it's a simple motivation for talking about mixed states. Let me directly go to our proposal to how to generalize the LSM to the open systems when you have a mixed states. So let's talk about that setting. It's quite a minimal assumptions. So we still use the hyperspace of the half integer spin chain. So the local hyperspace is say projective representation of SO3. For simplicity, let's always assume one half, like a spin half in this talk. And we impose the following two property. The first one is just a symmetry, just like before. In the pure state setting, the symmetry is imposed as your symmetry operator U act on your state, give you a phase at most. Here, we need to be more clear about that because there are two notions of symmetry in such setting. I will comment in a moment, but the notion we use here is often referred as weak symmetry. So we impose that the density matrix is invariant under the conjugation of the symmetry operation. Okay, that's the first assumption, which is just the same as the before symmetry condition. The second is new. We further assume that our state described by this density matrix is short-range correlated. Here I'm using a more physically motivated notion, like for any local operator OJ, OK, the connected correlation function should decay exponentially. If you are more interested in kind of more universal description, you can say the conditional mutual information decays exponentially with respect to the size of the middle part. Okay, and okay. I'm going to impose conditional information. It's more closer to the, well.
Forget about the correlation. That would just be mutual information.
Let's say spontaneous symmetry breaking. I don't want that. So mutual information. Oh, yeah, that's right. Okay, but I can exclude spontaneous symmetry breaking in the first place, using the first line. Well, yeah, I hope to use some kind of recovery map, so that's why I impose conditional mutual information. But for 1D, maybe mutual information also works. But anyway, if we want to formalize it, let me impose conditional mutual information.
Does the second condition sort of follow from the first one, that you don't have some
not really. For instance, if I happen to be a pure state, it's not excluded by the first one. But for the pure state, if it has symmetry and the spin 1/2 representation, I will have, say, power law correlation according to the original LSM. So the motivation of the second condition is trying to impose my state is actually meaningfully entangled with the environment. So you decohere those kind of a quasi low range order. What I didn't see the, okay, so for the spontaneous symmetry breaking, that's one example which you can exclude here, or that's maybe just accident. Yeah.
I mean, something like keep state of the Eisenhower that we still have a weak symmetry.
Like one-dimensional? Sorry.
But 2D, you know.
Yeah. Well, yeah, but okay, I think this is safe, right? So instead of talking about CMI, which I won't actually talk about in this talk. Okay, good. Our claim is, okay, at this point, you cannot talk about Hamiltonian because I didn't give you one, and intrinsically you don't really have to have a Hamiltonian for such kind of description. The basic idea is just to find another quantity to quantify the anomaly here. So the another quantity we use is the entanglement spectrum. So just so the entanglement spectrum here just mean the eigenvalue spectrum of the log of the density matrix. So we claim that the entanglement spectrum has to cannot have a unit gap minimum. So that's the same as the LSM. If you look at your lowest eigenstate of the entanglement Hamiltonian, which is a minus log rho, the next one must be very close to the ground state. So the ground state of the fictitious Hamiltonian, entanglement Hamiltonian, which I will comment in a moment. Okay. Yeah, I'm going to explain that. Maybe let me put all the slides here. So let me start from the first one. First, let me comment on the symmetry I use. So usually, when we talk about a symmetry in the quantum mechanics class, we talk about something commute with Hamiltonian. So it's like a dynamic thing. So if you start with some symmetric state after some time evolution, you end up with some symmetric states. Here, since I'm not going to use Hamiltonian description, I'm only referring to the states. So I'm basically using the Schrodinger picture. So I require my states is always symmetric along the whole process, along any kind of dynamical evolution on the channel. So I impose the weak symmetry. There's another notion called a strong symmetry. This terminology comes from the quantum optics. The strong symmetry basically impose, it's kind of a pure version of it. If you apply the symmetry operator on the density matrix, you again only gain a phase. So how to see the physical difference of these two? You can imagine you have a large system and look at the reduced density matrix of the subregime. Let's say large system has a U1 global symmetry, it conserves charge, but the small patch, it can exchange charge with the environment. So in this context, the small patch still preserves the U1 symmetry in the weak sense, but it does not preserve the U1 symmetry in the strong sense. The strong symmetry basically prohibits any exchange of the charge between the system and the environment. Okay. Yeah. You can see like if a diagonalized row, it's in the fixed charge sector. Okay. Yeah, to me, physically minded condensed matter person, weak symmetry is more common. Like in the grand canonical ensemble, you have a subsystem. The total system has U1 symmetry. The subsystem has a U1 weak symmetry. You can exchange charge. The second condition, the short-range correlation, is just, I have already said this, is trying to say is if the state is sufficiently entangled with the environment. Okay, now let me explain what is entangled spectrum. Entangled spectrum is the spectrum of the entangled Hamiltonian. Actually, Hosho explained this a little bit yesterday. You just imagine your density matrix can be written as e to the minus k. For the finite dimensional case, it's always legal to do so. And then you call this k entangled Hamiltonian. So it's kind of a fictitious Hamiltonian at temperature 1. Okay. It's entangled Hamiltonian or the spectrum of it has many applications in condensed matter. For instance, the Li Haodan stuff, and also King and the collaborators has paper about how do you use the entangled Hamiltonian to retrieve the chiral central charge from a single wave function. So it has interesting applications in condensed matter. And why do I choose that? What's the motivation of using that? So there are many ways to phrase the LSM in the open system. For instance, our paper is not the first one. Actually, the paper by this group is the first one, as far as I know, in the literature. So what they propose is they propose to generalize the LSM theorem to system described by Lombardian operators. So it's like an open system, but continuously interact with this environment, and the environment is like a Markovian. So that's their proposal. So if they impose the symmetry for those jump operators, they conclude the Liouvillean gap have to be gapless. So the rate to approach the steady state has to be constrained. Well, but I actually, for myself, I'm motivated by their paper, but while reading their paper, I found I'm not satisfied by the proposal, because I want something more general. I want something independent of the modeling of the environment, since as far as I understand, the anomaly is about the hyperspace and the symmetry, so it shouldn't assume too much about the environment. So that's my motivation. So the entanglement Hamiltonian definition is kind of completely general. Just hand me any density matrix. I take a log. Another personal perspective on why do I like the entanglement Hamiltonian is coming from the operator algebra. So in the operator algebra, there's a famous and also very important Tomita-Takasaki modular theory, where they define an intrinsic dynamics for each state. So if I only give you state, I didn't give you Hamiltonian. How do you define or quantify some kind of dynamics on top of it? So the idea there was they find a way to generate a operator automorphism, which sends you any operator to another operator by some kind of evolution. But this evolution is generated by the entanglement Hamiltonian of the local patch, for instance. Well, you can also well define this even when there's no density matrix description, like in more general phoneme algebra. So in the spirit here is when you don't have a Hamiltonian, or the Hamiltonian is not a good notion for local physics, the entanglement Hamiltonian will replace that. So we can just substitute that for any statement about the Hamiltonian and try whether it works. So that's another of my motivation to do that. No, because when we talk about the density matrix, we are not necessarily have a Lombardian operator associated with that. So it could come from something in some environment which is not Markovian. So like a general channel. I still think they are quite different things. The Liouville gap describes how fast it equilibrates to the steady state, but in time spectrum, apparently it doesn't have that interpretation. Yes, actually, yes. Yeah, I'm going to use the full operator to play with. But for the first statement, the first part of the result, I only needed a spectrum. Sorry, this proposed entanglement LSM theory. Well, we didn't prove it, so maybe it's a conjecture. Okay. Well, but I will use it for the second part. So. Well, for those who are familiar with the energy or holography, entanglement Hamiltonian is a natural thing to consider in the like full quantum version of the Bekenstein-Hawking bond. That's the key of the success there. Okay, let me present a simple argument why I believe such kind of proposal may be correct. So let's think how do we generate a density matrix that satisfy all the conditions. One simple way is to consider a spin chain. This is, A is the spin chain in question, like the spin chain we are interested in our theorem. So it's spin 1/2. But let's imagine it coupled to the environment. The environment happens to be another spin chain. So that's B, an identical spin chain, same hyperspace. And we first couple it with a strong anti-ferromantic coupling. So basically just J S dot S, and we favor spin singlet. So let's put a minus sign, minus J S dot S. So everybody knows the zeroth order, the ground state of this system will be a product of EPRPS, product of singlets. Is like a singular point. The density matrix of A is just identity, is maximally mixed. the identity has an internal spectrum that's very flat. So all degenerate eigenvalues. Okay, that's the zeroth order answer. And the true question is when we really consider actually couple, there's some non-trivial coupling along the spin chain, like there's some interaction here, interaction there, interaction here, interaction there. What's the highly degenerate internal spectrum look like after this coupling? So do you lift it completely? So like one ground state and the other excited states, or you resolve the huge degeneracy in the fashion of like gapless, like a CFT. So that there are two possibilities. I mean, there are two natural possibilities. So which one is the accurate is the actual one happens? So our theorem predicts you cannot have the first option. So whatever Hamiltonian you impose along this line and that preserve the symmetry, it won't fully lift the degeneracy like with one unique ground state in the bottom. Okay. So that's what we want to show, but here I only show it perturbatively. So what do I mean by perturbatively? I have a strong anti-fragmentic coupling. So let's say the singly triply gap I denote as delta. So the large energy gap, and then I apply a Hamiltonian HA, which is small in the sense like say operating norm is small comparing to delta, or the energy scale of this Hamiltonian is small in terms of delta. So I can just do the quantum mechanical perturbation theory, like a textbook. I simplify the formula a little bit. I already projected to the first excited states. So the first excited state will have to flip two singlet to triplet just to preserve the total SO3 symmetry. And according to the textbook formula, that will be the first correction to the state will be proportional to the HA plus HB, the delta H, the HA plus HB act on the ground state and divided by the energy gap. Well, I ignore the projector to the second, to the excited sector, so maybe slightly different from the textbook. But that's, I do it intentionally because for this simple formula, you can rewrite as a some kind of imaginary time evolution applied to your EPR states. So it's a maximum mixed between A and B. So it's kind of, if you know this notion, like thermal field double at temperature equals infinity. And you apply imaginary time evolution, E to minus beta A to this, E to minus beta B to this. Okay. Go ahead. Oh, I just, okay, yeah. I just, you don't, it's not necessary. It's just convenient because we all know for gap to the ground state, it has short range correlation. So it automatically satisfies the second condition. Sorry, I forgot to mention that. Yeah, I want to start with some states that automatically satisfy all the conditions, I assume, and show that has the property I want. Yeah, yeah. Thanks for this question. Yes, yes, yes. Yeah, now I have the states, so I can compute in time Hamiltonian. Okay, so this super simple is slightly regularized EPR pair. So you get the reduced density matrix for A part, and the in-time Hamiltonian will be proportional to the actual Hamiltonian you impose on the A side. And the temperature will be, the inverse temperature will be delta inverse, so the temperature will be delta. So it's a super high temperature because delta SU is big, so it's a large gap there. Question?
For generic case, how can you guarantee that you think Hamiltonian is a short range Hamiltonian?
Yeah, that's yeah, I can. Okay, that's a very good question. That's the key technical part of the thing. So our conjecture is actually when you have short range correlation. Sorry. We hope to prove this condition leads to some kind of locality of the entire Hamiltonian, which means it's the sum of terms which only have sum of terms that only have exponential tail. So we hope the exponential tail in the correlation function will imply that, but it doesn't really go to a quantum information proof. Yeah, that's why I want to assume condition motion information. Yeah. Equals 0, there's all the result by paths. The entire Hamiltonian is strictly local. But we want to slightly lose that to exponential tail to be more physically relevant. But it's really hard to prove the operator statement. Yeah, it turns out to be an open question in the quantum information. Many people work on it for many years. There's no counterexample. We run many numerics, but well, just to make ourselves comfortable. But yeah, there's, I mean, as far as I know, I didn't know any counterexample. Okay, yeah, for this perturbative argument, now we end up with entire Hamiltonian proportion to the actual Hamiltonian. Then for the actual Hamiltonian, we know its spectrum is gapless in the bottom. So that's a simple argument. That's the intuition for that. We also have a weak coupling argument. So this is strong coupling limit when you have a strongly coupled two chain. But you can imagine a weak coupling limit. You start with j equals 0. That you have two, say, gapless spin chain, and try to couple it with some relevant operator. That also goes to something related to that. That's actually according to Hauscher, Xiaoliang, and Andreas Ludwig's argument. So when you have some two CFT and couple them with relevant operator, you expect the reduced density matrix is like imaginary time evoluted Ishbash state or the maximally mixed state here. Okay. Anyway, we failed to prove the conjecture. But it turns out to be a useful conjecture in the sense that we inspired by the entanglement LSM, but not really rely on its validity. It's just like you impose ADS-FT, you get some interesting inspiration, but you can state some statement like a chaos bound independent of the validity of the ADS-FT. So we propose the following detection of the LSM anomaly on mixed state. It's an independent result, and it's collaboration with Shenhan Jiang's group. And we kind of have a proof for that. Okay, here's the statement. That's the second result of this talk. We define function f theta. This f theta characterizes how a symmetry, the expectation value of a symmetry operator. Okay, this rho is the density matrix that satisfy all the requirements I impose. SO3 is symmetric, U1 translation symmetric, and the short range correlated. And my prediction is if you evaluate this operator is just taking the one preferred direction in your SO3 symmetry, let's call SZ, and compute the total SZ. So it's not a twist operator, just to clarify, it's a total symmetry action. So e to the, then you make it a unitary operator, e to the I theta as total, and take the expectation value of it by tracing, and further we only care about the magnitude, so we take absolute value. We define such function to be e to the minus L f theta. L is the system size. Okay, I will.
System size is like full prime.
No, I don't need that.
But if you think about generate like charge 1-up state, after 2-pi rotation, whether there's L dependence already.
Yeah. I will justify why I put the L dependence there and why it's like a volume law. Yeah, L is the system size, and I want to, for instance, to well define this function, I take L to infinity and extract the leading term.
I thought L is not
I'm sorry. Okay, the prediction is f theta cannot be smooth over 0 to 2 pi. So first is a periodic function because the sz is like the difference between different sz is just integer, so it's a periodic function between 0 and 2 pi. But we predict for rho satisfy all the properties, this function cannot be a smooth function. It has to encounter some kind of singularity. It could be a cusp, it could be a corner, it could be two singularities, but it cannot be smooth. So that's a prediction. Okay, let me make a few comments or like the intuitions. So first, let me clarify what's the meaning of this operator. So I want to first emphasize that the absolute value is just put for convenience. You can just pick out it and say we care about the real part, the magnitude. So our quantity is actually a linear function of the density matrix. It's a physical observable. So what it reflects? It reflects the statistics of total Z. So it's related to the full Kantian statistics. So what you do, like in say variable atom experiment, you have some kind of spin 1/2 system roughly, and then you take pictures. The picture will tell you up or down, and you collect the samples, and you can calculate the total SZ, and you also calculate the sample-to-sample fluctuation. So you can get all the moments of SZ, and that's equivalent to the data here. So we have e to the I theta SZ for any theta. So that will be the same amount of data. Of course, for finite many experiment, I cannot get a like very sharp function. It will be smooth, but you can see it become more and more sharp in the picture when you have more data. System size, for instance. Okay, so this quantity reflects the statistic of total Z. So our prediction, you can say, is about the statistic of SZ. So it's really experimentally relevant. Okay, the second comment is this operator, if you purify the states, let's say using the same purification, you have a spin chain, you have a canonical purification using another spin chain, and they form some kind of states. Here I'm drawing some picture, but you can just imagine it's a big pure states. Then I apply the symmetry rotation for A. So if I apply the symmetry rotation for the whole system, I get back to the state. But if I apply it to the subsystem, it will encounter some like a mismatch across the boundary. So it's an extensive cut. So we expect in this case, the area of the box, but it's actually the volume of the A. So it's proportional to L. That's why we put L there. So this is the motivation. Okay, so you can see we are calculating disorder operator for some pure states. That's the same thing. And not.
This to a random calculation, this corresponds to domain of free energy.
Yeah. If you, yeah, you can see that like, yeah, if you put the Ising model, you put something. That's the traditional story. That's why there's an area law. Good. The third comment is if you are a fan of the strong weak symmetry, our quantity measures the difference between strong and weak symmetry. Because if it's a strong symmetric, it will be always 1. But if for weak symmetry, it's not 1, it's a non-trivial function, and our prediction is there's some non-triviality in that function. Okay. Now let's give some intuition. And this intuition is drawn from the entanglement LSM, like why we first come up with this quantity. So let me basically trying to explain the physical meaning of S theta. Okay, so if, just assume if, so it's not a proof. There's a actually better proof, but let me just explain the intuition. If this entanglement Hamiltonian resembles a CFT Hamiltonian, then this e to the minus beta, sorry, e to the minus k is a thermal partition function of CFT. Then what are we calculating? So I'm now here using Q denoted charge, which is the total SZ, but in general, we can make a more general arguments independent of the spin system. It could be a like fermion system. So what it really calculate is a partition function on this pink colored region. The system size is L, the temperature is beta, beta is 1. And the point is when we take thermodynamic limit, L is much greater than beta. So it's a high temperature thermal system, like a passing integral, and you insert a symmetry operator, e to the I theta q, unitary rotation. Okay. So what's the meaning of this? So what does this line do? This line, literally, it tells you if you have a charge, say, like something carry spin z, or something flip the spin z, yeah, or something in a electromagnetism, something carries electric charge. So if you have an operator that carries charge going from here to there, you should get a phase. So that's the definition of this. Okay. Next, we play with the Cadiz game. So we do a modular transform. That's allowed for the CFT. It's not allowed for general system. And that's the main difficulty to really construct proof. But here, let me just say heuristically, we consider CFT, and this, we can rotate the picture. It's like a space-time rotation. We are passing integral over this picture, so which is equivalent to passing integral over this picture. The model transformation is just a way to change the quantization. So here, I'm quantizing along this Cauchy slice, but here I'm quantizing along this Cauchy slice. The key is now we are encountering a system with system size beta, which is finite, but the temperature, the inverse temperature L is very large, so it's a low temperature system. And the symmetry operation, e to the I theta q, now becomes a symmetry flux. As we said, we have an operator across this line, we gain a phase. This is exactly what a symmetry flux do for a operator going around your system. So the picture now is we are calculating basically the low temperature partition function for a system with symmetry flux threaded. Okay, that has a good physical meaning. So you can just forget about all the excited states, just look at the ground states, and that will be denoted as E theta. So the ground state energy for such CFT with flux threaded, I will call it E theta. And you will have a thermal factor in front of it. It happens to be L, because space and time changed. And what our theory, or what our proposal is, there's actually a level crossing for the ground state energy. You can actually imagine that from the simple example like free fermion. The level crossing reflects the fact that at theta equal pi, you have a zero mode in the middle, so you have to choose which one you go. You can go up or go down. So there's a level crossing. Or in CFT, insert a general, boson, free boson, you have some, like say, vertex operator whose scaling dimension scale quadratically with theta. So you have a quadratic function here, but you have to repeat the same story for the theta around 2 pi. So there will be a crossover here. Independent of this certain examples, you can make a more general argument. Why would you expect crossover? This is literally because the anomalous symmetry we impose. So what we do from here to there, we insert a 2 pi flux. So here, go there, they differ by 2 pi flux. And we already showed that 2 pi flux of the SO3 carries momentum. So this state and that state has to be orthogonal. So they cannot be the same state. So it cannot be a smooth path connecting these two because they are orthogonal states. So that's what anomaly gives us.
So this is only for non-abelian. What happens for, say, a fraction of polynomial size 81 translations?
Yeah, I think that, well, I don't, well, it works for, you don't have, we didn't really use the full SO3. We only use the U1 cross Z2 part of it. So that's the U1 around the SZ. And the Z2 is like spin flip thing.
So I guess fractional polynomial type being
fraction quantum hole, that I don't know which anomaly I should talk about, like chiral anomaly.
Or let's say you have U1 fractional field, filling constraints.
Filling constraint.
Maybe remember U1 was.
Oh yeah.
U1 is not working on
I think you are referring to some kind like Oshikawa stuff. Yeah, you're right. Like you can have a U1 and the fractional charge of that, and that also works. It's just follow whatever you're familiar in the pure states. You can run the same out. Because after we rotate, it's actually a pure state. Okay.
So why do you need to assume it's a CFT CFC? You just need space time should be symmetrical. Is that all you need?
I just want to be safe, like the way to exchange the quantization. I'm not sure Lorentz symmetry maybe not enough if there's a subtle issue about the spectrum of the dilation operator. If it's continuous, there's some not very weird theory. Yeah, so, to get some intuition, I can assume as strong as I can. Yeah. Anyway, just get the intuition. Is it clear? Okay. Okay, so this field theory argument is good source for the intuition, but it's not for proof. We can actually prove this if we need to assume something like for short range entangled mixed state, we assume there is a matrix product density operator representation. That's a kind of commonly assumed in this business. If there exists such representation, that's native in the lattice. So this basically lattice side, and you represent your density matrix in this form. So there's a MPDO for each side, and you can track that, and you can compute the trace of it. That will be just contracting without the red dot, but you can also compute our quantity by inserting e to the I theta sz for each side on the physical leg. So that's the picture of the quantity in terms of MPDO. Then what we really want to show is that you can calculate this using the transfer matrix method. The transfer matrix method, the transfer matrix defined to be, you regard this leg tracing as the first thing you do, then in the end you trace the internal leg. So this will be a transfer matrix. So and then the quantity f theta will be basically the eigenvalues, the magnitude of the eigenvalues of the transfer matrix. So what we want to show is when you increase theta from 0 to 2 pi, there is some kind of singularity for the transfer matrix. That's the basic picture part of our work. I do have a backup slides to explain more details, but let me just say we managed to do so, like translate all the intuitions into a tensor proof. Okay. So let me summarize this talk. So I start with a slow introduction, explain how the quantum anomaly constrains many things, like the pure states, and how it constrains our 1D mixed states, how it entangle with the environment. So that's the LSN entanglement proposal. Then I showed that it also provides non-trivial predictions for the statistics of spins. And in the third paper, I didn't have time to explain. We also show that this kind of way of thinking, the anomalous symmetry constraint on the 1D reduced density matrix also provide new insights for the detection of 2D topological states. So where the anomalous symmetry is indeed coming from 2D. So like Z2 SPT provides you an anomalous symmetry on the boundary. And using this kind of argument, you can find a novel detection for the 2D topological phase. Yeah, here's just a question, like if this kind of thinking the topological constraint on the mixed state, does it have any application in the quantum, similar to quantum computers? Like maybe there's a circuit that preserve all the symmetries. The symmetry happen to have some anomaly. Maybe we can already know something about the the final states without looking into the details of the circuit, something like that. That's what I want to discuss with the audience. Okay, so with this, let me thank you for your attention.
Yeah, thanks for the very nice talk. Hi. Yeah, thanks for the very nice talk. So could you comment more about your second point about providing non-trivial predictions? Because as far as I understand, like what you're saying is that the characteristic function of the PDF of charge has some feature,
Yes.
but in terms of the actual snapshots, what am I going to look for?
It's just saying that, let's say, this one. Yeah, it just say if you compile the moments
Yeah,
and resum into this,
yeah.
with more and more sample, the function will look more and more sharp in the middle.
Right.
So I don't know how to translate that directly into like certain constraints on certain moments, but that's collective constraint.
I mean, the only thing I can think of is that you're saying that the moments decay slowly because you're saying,
Yeah, maybe.
yeah, because because from the Paley-Wiener theorem, you have like slow decay of these moments, right?
Yeah. Actually, you can derive something like, okay, so here's a singularity. So first, for general system, we don't know where is the singularity, but when you impose reflection symmetry or time reversal symmetry, the singularity is at pi, at theta equal pi. Then you can calculate the derivative of this function at theta equal pi. You should expect something very large, which is about the SZ expectation value, but on a twisted ensemble.
I see. Thanks.
So maybe you can test something there.
Okay, thanks. And then one more just very basic general question about anomalies and LSM. So like translations and momentums were very key to this theory.
Yes.
Is that necessary, or are there versions of LSM that don't require translations? I'm just not familiar.
Yeah. So that's a good question. Yeah, okay, I'm also not very familiar, but what I know is that you can talk about, say, some Z2 symmetry that is anomalous in the sense that it cannot be represented like factorized on the local hyperspace. Like some Z2 symmetry can be only represented as an MPO. So let's say the edge of the Z2 SPT. So they also have non-trivial predictions like that. So that's the part of the work I didn't explain. So in that case, is the Z2 flux itself carries Z2 charge.
But in that case, it's like kind of I can think of mainly as like because density matrix, 1D density matrix, if it's given as a identity plus some anomalous one form operator, that already tells you that entanglement spectrum should have some degeneracy of 2, and it's kind of like that, or is there something more than that?
Okay, so what you said has one factor of that, like I mean, for let's say Z2 SPT. So let's be more concrete. And give you 11 Gu wave function and do the reduced density matrix, which has areal and it can be transformed into 1D reduced density matrix. It has anomalous Z2 symmetry. Okay, let's talk about this. And it has emergent Z2 strong symmetry, like coming from the one form symmetry. You can understand it as you obtain this Z2 SPT coming from anion condensation of this double semion stuff. Yes, that one give you one prediction. That's like a string order like operator. People also talk about that, but it also give us more. So there are more than that one form symmetry. Yeah.
So if I understand correctly, all of this applies to the kind of completely mixed state. So in what sense can you hope for any kind of non-trivial implications?
Yeah, good question. I think okay, let me give you good. Okay, that's a good question. Nice. Yeah, I like it. Let me show this. Okay, let me use this. This is maximum mixed if you look at A. You can actually forget about all the others. Just look at the first one. This is singlet. Now you imagine you apply SZ rotation for this one and apply to pi. So you get -1 for the spin down, +1 for the spin up. So you turn a singlet to triplet, which has 0 overlap with the singlet. So you have overlap equals 0, you take a log, it become a cusp. That's a non-trivial prediction for f theta. So you literally calculate this, you get a cusp.
Assuming you have an access to canonical purification.
Yeah, I'm just showing one example which answer the question. It works for any purification because I didn't touch B at all.
For the sake of time, maybe this should be the last question. Oh, yeah.
I have a question regarding the position of the cusp. So if I just consider the onset Z2 times Z2 symmetry and the translation symmetry, which is subgroup of the symmetry group you consider, it also has a LSM.
Sorry, say it again. Which symmetry? U1 cross Z2?
Z2 cross Z2.
Oh, Z2 cross Z2, yeah, also works. That's right.
Yeah, it seems it also works. So that seems to imply that there should be a cut at theta equals pi at least.
And that's a very good question. That's actually the motivation of our, unexplored, the third paper I talked about. In that case, you don't have a continuous variable to talk about, so you can't see it. So you only have discrete point. Then what can you say? You cannot justify there's a cusp or not. So we've devised something new, like some kind of related to degeneracy here.
I see.
For the Z2 one.
Yeah, thanks.
All right, let's thank the speaker again.